I was born and raised not far from here, in the city of Bangalore, over half a century ago. My parents had the habit of spreading a mat on the garden after dinner so that we could watch the night sky. And I loved spotting the planets, an occasional meteor, even artificial satellites that to me seemed to wind their way through the stars. It was really, really exciting when a comet showed up. So it shone brightly, and its tail extended wide and long across the sky. I vividly remember doing a painting in watercolors with our mango tree in the foreground. That's not my painting, that's someone else's. I was born the year after Sputnik was launched. The advancement of science were thick in the air. Yuri Gagarin and Valentina Tereshkova, who were the first humans out into space, were my childhood heroes, and I fantasized about being a scientist on a spaceship. When I was about 8 years old, my parents gave me this children's book called The Atom, and it had a beautiful illustration of the famous Rutherford's gold foil experiment, where he stretched a gold foil and fired energetic particles at it to see what came out. Most of the particles went through, but some particles bounced back. And that completely changed how people thought about the atom. They realized that most of the mass of the atom was concentrated in the center. I thought that was so cool. And it also brought home to me how science works and how scientific thinking works. So the refusal to accept anything without test or trial, and the capacity to change one's conclusions based on the evidence, as Jawaharlal Nehru put it so evocatively. So, among my memorable after-dinner mat in the garden moments was the breathtaking view of the Milky Way. But little did we know at the time that at the very center of the Milky Way, scientists would find a giant black hole. So when people think about black holes, they think about emptiness or very dense things. Black holes are chunks of space-time from which even light does not escape. So we can get an intuitive feel for what black holes are if we remember some of our high school physics. So if you remember that you throw something, it returns back to the ground. You throw something faster, it goes further but still comes back. But there is a speed, quite a high speed, at which if something is launched, then it will escape. And we call that the escape speed, if you remember. And for those who like formulae, I've put the formulae up there. So now, if we do a thought experiment, and imagine that we take the whole mass of the Earth and squeeze it. So then, we keep the same mass and squeeze it, and so the distance from the center reduces, and so the escape velocity increases. Now, suppose we continue this thought experiment and squeeze it so much that the escape velocity becomes the same as the speed of light. So then nothing can escape from such an object, and that is what we call a black hole. And it turns out that for the Earth, for the mass of the Earth, we need to squeeze it to a marble size in order for it to turn into a black hole. Now, you might say that's impossible, and that's perhaps true. But the interesting thing is, if you do the math, then the more massive something is, the less impossible the squeezing feels. So, for instance, the sun is 333,000 times as massive as the Earth. And if that has to be squeezed to become a black hole, it will have a diameter of about 6 kilometers, which is which is a volume, which is like quadrillion times that of the marble-sized Earth black hole. Think of Gargantua, the fictitious black hole in the film Interstellar. That was given a mass of 100 million times the mass of our sun, and that feels even less squeezed. So what we did not learn in our high school, and what we perhaps should learn, is Einstein's new way of understanding gravity. So not as a force between two things, but that all masses result in space-time, the very fabric in which we and all this stuff sits, curves. So my mass, your mass, this building, the Earth, the sun, all of these masses curve space-time. More curvature, if more mass. Now, what about the black hole at the center of our Milky Way? There was a long-standing suspicion, and that which lasted decades, and that was followed up by scientists who had access to enormous telescopes to capture the infrared light from the very heart of our Milky Way. And they imaged stars in the heart of our Milky Way to try and see how these stars move. So this is their finding. So the multicolored splotches that you see there are stars. The number on top is the date on which the snapshots were taken. So they took regular snapshots one after another starting in 1995 and put them all together to make an animation. And the white star is not a real star, it's just a symbol to mark a position, and you will see why. And they put them all together to determine how the stars move, and this is how the stars move. So they're not moving in straight lines, they're not moving randomly, they're moving in elliptical orbits, but interestingly, all around the same focus, which is marked by that white star. So that's very reminiscent of our solar system and how the planets move. And if we do that similar math, it turns out that there is a very heavy dark object in the center at the position of the white star, and it has to be small because the closest approach star doesn't collide with anything, but goes along merrily on its elliptical path. So this thing has to be really compact, which means it's got to be a black hole. So there's a 4 million solar mass black hole in the center of our Milky Way. And then later, by an entirely independent method, and for the engineers and physics students here, it was a method by which the Fourier transform of the sky was measured at millimeter frequencies and then inverse Fourier transform to get the image. We got the silhouette of a black hole, of the black hole that Ghez and Genzel and so on measure. And even more interesting, perhaps, is that the computer simulation, which tries to encapsulate our physics understanding in what happens when stuff comes close to a black hole and swirls around it and so on, that is also consistent with the results from both the silhouette and the work tracing the stellar orbit. So this is the power of science. The whole process is about constantly testing our conclusions, either by replicating experiments or by doing the same thing with an independent method. So the two methods, the business about tracing stellar paths was done by two different groups with two different telescopes in Hawaii and in Chile, and they got consistent results. And this was an entirely independent method, which again got consistent results, and all of them affirm Einstein's new way of looking at gravity. Mind you, if there was not consistency, it's not that we would be upset. We would just be intrigued and ask, say, so what does this inconsistency tell us? So that is how science proceeds. So it turns out that not only does our Milky Way have a giant black hole in its center, but every galaxy we have looked at does. And so this is quite an ordinary characteristic of galaxies. And what that means is that sometimes when matter comes very close to this black hole, it's pulled in, swirls around, gets accelerated and heated, and therefore glows. And it glows with a power that is more than the power from all the stars of the galaxy put together. So these become really bright beacons in the sky, which light up the universe to vast distances, because we can see them from very, very far away. And they tell us how vast and how big our universe is, and we see these giant black holes that glow like this right up to early times of the universe, even a few 100 million years after the beginning of the universe. And not only that, some of this material which is swirling around doesn't actually plunge in, because it's so ionized and magnetic fields are created that some of that material is launched out in the form of two jets of plasma, which then even sometimes are launched with such high kinetic power that they launch out at speeds close to the speed of light and reach into intergalactic space, which is what we see here. And the stars of such galaxies could look quite nondescript, like this example, but it spews out these jets of plasma into intergalactic space, and if we zoom in, we see the jets actually coming out like this from the center. And using that same technique of very, very sharp imaging, which showed the silhouette of the black hole at the center of our Milky Way, which is imaging so sharp that, for instance, if I was sitting here, I could read a newspaper kept in Delhi, or I could discern a mango that is placed on the moon. That is the kind of sharpness of these images. And so, again, they saw the silhouette of a black hole. So these are the two black hole silhouettes that we know of in the cosmos, which is the most direct evidence for their existence. And so this is a picture of a piece of sky that is about a 20th the size of the moon in the sky. And every dot and smudge on this picture, apart from the ones which show spikes, which are artifacts, but every other dot and smudge in this picture is a galaxy. So it likely has a giant black hole in its center. It had hundreds of billions of stars. Each star likely has a planetary system. So it tells you how vast our universe is. So no wonder that Carl Sagan called our Earth the little blue dot. This is a picture that Carl Sagan encouraged the spacecraft to take, and you can barely see our Earth there, containing all of humanity, but coasting along in a rather lonely space. So that is a zoomed out picture of our little blue dot. So the sky is a universal laboratory. It's for everyone to explore, not necessarily only for pushing our scientific understanding, but also as nature lovers to understand nature. So what we know from this universal laboratory is that there is no planet B. And that is why a group called Astronomers for Planet Earth wrote this letter to the world saying, we astronomers, astrophysicists, global citizens recognize the urgency of the climate crisis and our impact on it. We also recognize that we have the power to change our current practices. Comprehensive scientific evidence clearly demonstrates that we are living in a climate emergency that calls for urgent action. So questioning and scientific thinking is necessary not just for scientific research, not just to excel in whatever pursuits we are engaged in, whether science or otherwise, but also for life itself. We need scientific thinking in order to live intelligently, in order to be effective in a democracy, and in order to save our planet from the current catastrophe. Remember that the visionaries who were the leaders who shaped this country were not scientists. Gandhi, Nehru, Ambedkar were not scientists, but they were people who made scientific thinking a way of life for themselves. And so, you, the youngsters, are the stewards of our planet and the parents of tomorrow. It is really important that you question everything around you. Not just questions like why the sky is blue, or why the moon acquires a copper color during an eclipse, but also why there is poverty and inequality, and why do humans wantonly light pollute and destroy the heritage that is our night sky. Look at how our lighting functions. Most of it wasteful, upwards, not where it is needed. So hopefully tomorrow will come. Remember that all of these things are connected. When I was in Mangaluru half a century ago, I could see the Milky Way here. But you have lost it, and you need to bring it back for your children. So there needs to be, for example, scientific thinking in our lighting. So understanding how lighting should not be wasteful, it should be efficient, but it should be pointed where it is needed, and it should be for everyone's need, and not for everyone's greed. So the night sky and its loss is a metaphor for the current crisis we are in. So let us heed what Gandhi said very scientifically and very evocatively, that the earth is sufficient for everyone's need, but not for everyone's greed. Thank you.